Awesome. Well, again, welcome to this talk. I am Tim, he, him, and all of that good stuff. I am a software engineer by training. I've run biohacker spaces. I've written lots of software, worked with lots of scientists, and seen a lot of code in my life. And I've seen good code and I've seen bad code, and most of the bad code, honestly, is from scientists, and that's okay. You don't need to be a good programmer to be a good scientist, but it definitely helps. So if I get to share my screen here, and like watch me completely fail to use a computer despite the fact that I have like 10 years of software engineering experience, it's amazing what you can't do with a degree. So yes, funny open slide. Polymerase, the world's most modern open source Synbio Software Library. And the reason why I have a spaghetti monster here and my little gopher friend is that the gopher is actually Golang's overall mascot. And when we first got started, a student group asked, how can we help? And I was like, well, I can't really do graphic design and we should have a mascot. So they eventually made this little gopher with scissors and DNA. It was pretty cute. And we're actually going to get, like, I hired someone to, like, I commissioned someone to actually make us a new mascot based on the flying spaghetti monster. Because I really think that synthetic biology has an issue with not being creative enough. It's an incredibly expressive medium. And you'll find that in my work, I have this real dichotomy between imagining what could be possible and having this sort of rigorous, we can't do anything until the software works. And that's sort of the basis of my talk. And so, again, I am Tim. I'm something of a mad biologist myself. And I pitch people stuff like Tide Pod trees and flying seaweed, just because it's cool, and there are commercial uses for these. Um, and so this is a kind of an overview of how I got into this. Is this SpongeBob meme? So people will tell you synth biosoftware isn't that bad, but look at GenBank. Look at all the papers that say code available upon request, the abandonware, the no unit testing or documentation. It runs on my machine, and the mountain of spaghetti code. And you will find that even the most prolific people in the field release code that you can't really read. And to give you an example, this was highlighted by Patrick Boyle, who is the head of software, or no, I think head of code base is what they call him at Ginkgo. And he was tasked with turning Ginkgo's incorporated their IPO documents into a string of letters that could be printed into DNA and made as a deal toy. And he was really excited with this task until he was told that he had to do it using a paper written first offered by George Church, if you've heard of him. And he was really excited until he realized that this was what he was going to work with. So George Church, one of the most prolific synthetic biologists in the world, in 2012 wrote this. And I don't understand it. It's supposed to be shifting bits around and turning DNA into, turning bytes into a DNA encoding, but you can't really tell what's going on. And this guy was, pretty upset that he had to do this. And that's sort of the standard for a lot of people is they hear about this really great idea, they see this really great paper, and they get all excited, and then they try to go and do it. And even from the cheap, literally free software perspective, in some cases, they still can't get it to work. And so that's kind of how Poly came about. All right. So the beginning of this is how a lot of Synbio stories start. I got a call from Keone Gandil. If you don't know Keone, he's one of the major contributors to Poly. He's kind of like a child wonderkind, but he's finally an adult now. But he used to be a teenager going to a lot of these conferences. And Keone had a job at Stanford where he was working for Drew Endy, who's a synthetic biologist there. And Keone quit his job at the beginning of the pandemic and moved back with his parents in Los Angeles because he didn't want to be alone in the Bay Area, just chilling in his one-room apartment, or his one-bedroom apartment. Didn't want to do that. So as Keone is driving down the California coast, I get a call from him, and he goes, "Hey Tim, there's no way to convert GenBank to JSON back again, and my BioPython script keeps breaking." Now, if you don't know the words JSON and GenBank, that's okay. But this is literally the most common data interchange format in the world, JSON. Literally almost every language has something that can read this natively. It's really easy to use. And then there's GenBank, which is what everyone uses for annotated sequences. things that hold, features, but it tells you from the start to the end of a certain feature, and this part of the sequence is there. Um, and there was no reliable way to go between the two, which is insane. The most common data interchange format ever doesn't work with the most common annotated sequence format. What? Excuse me? So my reaction was pretty much, lol, what? Like I like, sir. So I get to work, and it took me about 2 weeks, honestly, of me grinding at this problem. It turns out that GenBank as a file format is really old. The history is amazing. It's kind of lost the time. It was made as a human readable file format for sequences in 1978 by a gathering of people in the deserts of New Mexico. And there's no record of who these people are or what they were thinking when they made this. So I struggled for weeks just finding documentation, figuring out, how I'm supposed to write this parser. It was, I've written a lot of parsers in my life. I've written a lot of code that reads things. This was one of the hardest ones I did. The end product was like 900 lines of code, to parse, read, write, build the strings, do the input output of this. And this is kind of, this is the parse function. And that's the first 40 lines, but there's a lot more to it. Um, and so you'll see that, this is actually the earliest code I've made for this. So it's not as up to snuff as the stuff in the later bits of, I think, but you can see it's really just me taking a string, splitting it by line, getting all the meta features out, getting all the, annotated features out, and getting the actual sequence string. And you think this would be trivial, but again, an absurd amount of time. And so think about it this way. Um, the JSON parsing literally took me all of 5 minutes to set up. The GenBank parsing took me 2 weeks. Um, and this is the state of the world if you want to use GenBank anywhere. Actually, is you have to, if it's not in Python, you have to write a parser for 2 weeks and hope it works, and that's not acceptable. You can't just do that for a lot of people. So I decided to export it as a command line tool, and now you can convert as many GenBank files as you want to JSON. But that wasn't really readily available, to my shock and awe. So wait, no one can do Synbio because no one can parse GenBank. That was kind of like my wait, are we doing stuff? It was it was an existential moment for me. I was like, wait a minute, what's going on? So what the fuck? And we just began building more. Just me and Coyote, we've come up with a hashing algorithm. So for those of you who don't know what hashes are, they're essentially ultra compressed strings of information. So you can hash a file and it'll give you like a 64 character deterministic string, and you can use that as an identifier for your files and for your sequences and your strings. So now we can actually do plasmid lookup and sequence lookup, just hashing things, because we had to write a tool that would always make it so a circular plasmid sequence, because if you can imagine a plasmid, where you start sequencing can always change on a plasmid. The starting point, it's a circular thing. The starting point can change. So if you want to make sure that it's the right plasmid, you have to make sure that it rotates the deterministic point. And we again wrote that in 2 weeks, and we were just surprised again that it didn't exist. So we kept building stuff, and then we started just making sure everything was tested. So when I'm saying 97% code coverage, when I mean that if we change anything and it doesn't work, we literally have a script that will yell at us and tell us exactly what doesn't work and why, and we won't ship it until we fix it. And it's just a really nice safety feature, and is what makes Poly usable by other people. Isaac can probably attest to this, that if stuff breaks, he can tell us and we can figure it out. And that's not always the case with a lot of packages. So, and then even the examples in the documentation are tests. So this is actually really, really cool and really important. When you use other people's libraries, they write documentation, right? They'll tell you, hey, this is how you use it. Here's a tutorial, blah, 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 blah. And then they'll update the software, but they'll forget to update the documentation. And all of a sudden you have this documentation that doesn't actually do what it says it does anymore for the version. And there's a lot of ways to combat this, but the way we did it, and the way that I like a lot, is, let's see if it'll take me out here. Yes, great. Is that we can actually, we write our tests such that, this is a test. This is a very basic test, and all it does is it takes a FASTA, reads it, and prints it out. That's all it does. But the thing is that this is runnable from, I can't actually see because of Zoom. Get out of here, Zoom. This is runnable from the actual package itself. I mean, not the package, the actual documentation itself. So this is actually like a full editor that always updates every time we update the software and will tell us if it doesn't work. So our docs literally never rot. Everything that you see in our documentation, you can actually rely on, which again, super, super helpful. So if I wanted to change this to fastest sequence 0 and run it just to see if it works, let's see if it works. Come on, waiting for remote server. This is a live demo. Live demos never work. It's a curse. And it didn't work. I don't know why. Hey, but it did change. Yeah, see, Isaac's laughing because, dude, live demos never work. I don't even know what this FASTA file does. It's all on Keone. But if you go, oh, cool, it's a runtime error too. That is awesome. So as you can see, sometimes things break. But I'll tell you that at least according to the repo, this stuff works. I'm really interested to ask Keone why that didn't work, because he wrote this test specifically, and I really should have ran it before I tested it. But I made
it doesn't work because we didn't embed the FASTA file into the binaries that we ship.
We didn't. Oh, we don't do that. Then how is it getting the output right? Is it just reading it from
Cache?
the test?
It caches. Go caches it. We can just embed them though. But
yeah, we can embed them. Okay, cool.
That's in all your original examples, you didn't embed the test files, and I was just like, oh, I don't know.
I think I removed them so that the binary would be smaller. Does it literally just take the binary? I thought I was excluding tests.
Basically, in order for it to read that like data/base.fasta, it has to exist on the file system or embedded within the binary file system.
Yeah. But see the so okay, so I was hoping they were just directly running it from the repo itself, but you're saying they just take binaries. Okay, great.
They just take binaries.
Awesome. Well, yeah, live demos happened. First time doing this talk. Good job, Tim. Woo! Well engineered, I was saying. Yes. Well engineered. Obviously. So if I get back to my talk, oh my God, can I get back to my talk? Let's see. What? Oh no, I have exited out of my thing. It's okay. It's all like literally all WebZap stuff. Oh shoot. This is like most of my talk. Sorry guys, you're gonna see a lot of memes all of a sudden. No, that's still not it. That's money. Okay, I'm just gonna.
You're not sharing your screen right now.
Oh, good. I didn't want you guys to see this anyway, so that's perfect. Let's see. I don't know how. Dude, I can't believe we're letting me give a presentation. Who thought this was a good idea? Okay, great. Thanks, Sebastian. I heart you too. So this comes down to write code so that everyone can understand it. So if you guys remember like your like basic calculus class or your basic math class, you have a bunch of variables, right? You write your x's and your y's, you solve for y, and pretty much every mathematician names all their variables like this, right? It's just a single letter or maybe two letters, or like there's a delta in there. But this is code, and we can write words like regular people. So what a lot of ends up happening is that we have no single letter variables or mangled one-liners. We have a lot of comments, as you've seen earlier. And I'm really strict about this because you'll find that you can write a piece of code and you will understand it when you write it. And then 6 months later, a year later, you look back on it, you're like, what was I doing? It's almost like you're writing yourself your own cryptic, I wouldn't call it hate mail, but something not fun for the future. It's not fun to write code and then realize you don't know what it does later. So this is what I do in code review. Every time I see like a single letter variable, Keone can attest to this. He hates that I do this. I've read a lot of Keone's code. What is this? A variable for ants? No, and the thing is that you need your variables to have. I know this is like, why are you talking about variables, Tim? I thought we were learning about Synbio. Hold on. This is really important because if we don't have our software work, then we can't have synthetic biology. It's just, unfortunately, that's just the reality. And you can ask Cymergen because their software doesn't work and they don't have synthetic biology. And that's why their shares tanked 400% last month. So when you get to the variables for ants, it's one of those things where you do need code quality. You need things to work. You need to believe. People need to have some belief it's going to work. I almost believed that my demo was going to work. That's amazing. Usually I wouldn't have that much confidence with anything. So that's great. So if we're going on, how did this happen? Well, we started writing code and we started doing all this stuff. And like in March of this year, like I finally just shared it on the internet and we started forming a gang of random internet nerds. And gangs of random internet nerds are amazing because you have literally the whole internet to work with. You're not just like, oh, I have to work with this person at this fancy lab and their grad student and blah. Nah, dude, you can just get whoever you want to hang out with you, which is amazing. So we start forming this gang of random internet nerds, and this is kind of the deal, honestly. Um, we've made this amazing software package just by memeing and writing code together, and it's literally better than anything that's been put out by any startup or academic lab with millions of dollars. And the question is, why? How? What? How does this work? And it's really just comes to the fact that we're relying on people to push code in their interest. Keone pushes code because he wants it to be stable. I push code because I want software that works in the future. Isaac pushes code because Isaac, why do you push code? Exactly. Like, everyone has their own incentive for doing this. Some do it for glory, some do it for money, some do it for work, some do it for fun. But in the end, we all are a bunch of random internet nerds, and our hive mind of like only 11 people is somehow out software writing some of the biggest companies on earth, which is nuts. And so this is a blurry setup of all the contributors here. I couldn't get a better screenshot last night when I was putting this together at the last second. So that was the last slide, but that was blurry, but you should check out our contributors graph on GitHub. You can see what people have done. There's real accreditation for what people have done and how, what they've committed. And it makes it really easy to tell who's done what code-wise. And that's something I really love about it, because, in a lot of academia, people argue, oh, should they be a co-author or not? And my philosophy is, I don't care if you fix a typo, dude. You're a co-author as far as GitHub will say you're a co-author. There's literally one guy whose all his contributions are like updating the copyright year and fixing typos. And he sure as hell is going to be on our preprint. I don't care. It's important. So what we've done that I can remember at 12 a.m. the night before this talk, we have written parsers for almost every common annotated or non-annotated sequence format. We made a JSON schema for DNA sequences. Why are we the first to do this? I honestly don't know. It took us like a weekend. It wasn't much. We made the first open source hashing algorithm for plasmids that accounts for sequence circularity. We have primary design tools and simulation, code optimization, and DNA synthesis, and cloning simulation. And it's all fast and tested. And I'm not going to run the demo for this one because apparently they're not embedded, but I can at least show you the code if it lets me here. Oh, come on, Zoom. Get out of it. I don't care that I'm screen sharing. Let me switch tabs. It's so annoying. So here we have this is the overview and documentation for our DNA synthesis package. It goes over, the restrictions that DNA synthesis companies can have. It takes advantage of synonymous codons and protein sequences. Just quick overview. It has an index of all the functions we use in here and their sub methods of their type. And I'm trying to use my mouse from the wrong screen. Oh my goodness. This is rough. Here we go. So again, we have this nice, soon will be runnable example where we initialize a gene, just something to work with a simple string. We create a codon table. And what this does is it literally reads all the triplets and gets a frequency, because that's kind of what most people work off of, honestly. And then we optimize the sequence with the optimization table, and we run fixed CDS simple here. And it has a bunch of internal stuff that it looks for, like, for example, restriction enzymes, et cetera, et cetera. There's actually fixed CDS simple is a wrapper around a more complex fixed CDS function where you can pass it anonymous functions to filter out whatever you want. But this is like the same default that literally like 90% of all cases can fit. It's really easy. And then you get your thing, and it runs in like less than a second, which is great when you want to do thousands and thousands of coding regions to fix. And so we have, a variety of tools with good examples that you can use it's starting to be this point where my end dream, I don't know if it tells you, it kind of tells you what we're doing. My end dream is I do want to work in hardware. I do want to work in, the lab again. But the end dream is we need the code and data to do it. And so Allbase is sort of our way of replacing GenBank and Uniprot and Keg, I think it's Keg, by essentially getting a cross-reference database using the hashing algorithm I mentioned earlier to have GenBank in one part all in JSON, Uniprot in the other part all in JSON, and Rhea and a couple of metabolic mapper things, and I believe what's that fourth database that I'm being actually paid to put in there? I can't remember what it's called, um, but there's one that also includes bioassays. Um, and so we're getting to the point where we can almost do metabolic engineering and pathway querying all over all of Allbase, which is literally all of GenBank and all of Uniprot. So now you can say, hey, here's this organism on GenBank. Here's this protein I want. Can I get a metabolic pathway map for this and a set of instructions that tells me how to edit this thing to do that? And that's huge. And that's the first part for me. And the second is really protein engineering and ML ops, because unfortunately, protein engineering is mostly at this point machine learning stuff. And also machine learning stuff is really annoying to deploy. I don't know if any of you have worked with machine learning models before that aren't just like, k-means clustering and like basic traditional machine learning, but it's a pain in the butt. And it's not something that you should ever make a grad student do, because that's just mean, dude. Like, grad students are here to like have fun, do science, and they shouldn't be spending all day figuring out how to run TensorFlow on what is essentially an overglorified gaming PC. Like, you like that's not fair. They shouldn't have to do that. And so eventually we actually have a ribosome binding site calculator that's being in review right now. This is just more expression optimization stuff and genome engineering with CRISPR multiplexing. It's just, the stuff that's just coming through. And then how can you help? It's an open source project, anyone can help. But like all things, the easiest way to help is money. Can you please sponsor me at GitHub? I'm sorry. It's because it's kind of the truth in the sense that, I am the expert here. Like, I spend most of my time reviewing code or trying to find contracts or write contracts. And I really love some sponsorship, because at least then, I don't have to spend so much time working on essentially side things for clients. It gives it like, because you guys get to do all the fun stuff and then I have to review it. And it's like, if I get to do the fun stuff, I don't have to review it because I already did it. Like, it's way better that way for me. So if you want to save me from hours of code review, please check out my GitHub sponsors page. But also the real thing, use Paula in your projects. Tell me what you need. Just enjoy using the software. I mean, that's kind of like the real reason I did this. Like, I didn't do this to make money. I did this because I didn't like the way software was being done in the field, and I wanted people to feel good about what they wrote and to feel proud and that their software is going to last long. So please do what Friendzymes is doing. Use this in your project. Ask me questions. I have a whole Discord that you can come talk to, and they're really sweet. And they're from, again, like Friendzymes, every corner of the internet. We had one guy from Perth, Australia that was like, I want to go to this talk, but it's 2 a.m. my time. I'm sorry. So thank you for recording. Apparently he's going to watch this. I'm so sorry that you're going to watch this, but going on. Request features and review pull requests. Always ask me what you want, even if I'm like, no, I don't want to do that. Maybe someone will take it up and I'll be like, I guess I can maintain it. I can put some time into it. And just review pull requests. Even if you're not a real, if you don't consider yourself a professional programmer, you can just still be like, hey, I don't understand this. Like my take when I do code review is it's like editing a book, right? And I just have to be the dumbest editor on earth. I ask the silliest questions, even if I know the answer to it, mostly because I'm making sure that it's clarified for someone who may not know the answer for it. I understand what the central dogma is perfectly, but an amazing engineer who's worked in Go for like 10 years may not know what the central dogma is and may need a little nudge to make sure they know what they're doing. So if you have a biological context and you find, something like that where you're like, hey, it doesn't really explain the code or the biology, I love it when you tell me I'm wrong. I love being wrong because at least someone's telling me I'm wrong. And so the last thing you can do to help, again, but no, really though, money. So please go to my GitHub. No, I'm kidding. Okay, that's the end. And yeah, any questions?
I think we can look for the questions now, guys.
I think one thing that I would like to say more is about, because Poly it's have an interesting choice of language, right?
Oh, I have a story behind that too. Should I explain that, Isaac?
Yeah, definitely.
Okay, I'll talk about that. Okay. So as scientists, I'm assuming most of you are scientists. You've done scientific work before. You've likely used languages like R and Python and maybe Julia or MATLAB. I hope you didn't use MATLAB. But Sebastian's like, nah, dude, never, not even once. So these languages are scientific programming languages. They're kind of what's known as scripting languages, and they're really great for prototyping. They're really great for, saying, here's an idea. Oh, Keone's saying, Lua, that's Sebastian's language of choice. It's also a Brazilian language, so so but Lua's everything. Yes. Shill for your favorite language now before I continue this talk. Get it out, guys. What's your favorite language? Is there a learning bio with Poly guide? Wait, wait. I'm not even following the chat properly. What's going on? What is happening?
I basically asked if there was a how to learn biology with using Poly kind of a guide.
Kind of. We're sort of getting to that point. Not quite yet, though. We've gotten to the point where the infrastructure is almost there. Like, we've found a way. We've found a way to run it in the browser. And once we actually get that working, which I didn't know wasn't working, that makes it a lot easier, because now we can write example code where we can have a central document that's like, here's chapter 1. Here's how you do basic file input output. This is what the central dogma is. This is what you're looking at when you're looking at these files. And you can kind of go through the whole pipeline to the point where you could, actually design an organism. That is possible. That is in the works.
You know what we should do, Tim? Like, I've been harping about this forever, but obviously I'm trying to graduate, so I don't have the time to do it. But if somebody else does it, I'll be like really appreciative.
Of course.
Is take like the BioBuilder book and make like how to do everything in BioBuilder with Poly.
Maybe. I think there's definitely thoughts of me. Like, I've definitely thought of doing that, and it's on my mind. There's still some things to do before that. And again, if you guys want to throw sponsors on that and be like, hey, Tim, go make that book, totally will do it if people throw money at me. Like, oh, come on, dude. So the choice of language really came down to is you're seeing these scripting languages, and they're great for prototyping. If you're a new programmer and you want to put together a machine learning model or do some basic file, write your script, play with it, that's awesome. And it works in a lot of cases, especially in the smaller projects. But as soon as you need it to run on someone else's machine, you need it to run fast, you need to feel environmentally friendly because you're not burning your CPUs to death, you should probably use another language. And so when I started working on Poly, I wanted something where I could ship a command line tool that would work, something that would be very stable, re-releasable, well-tested, and have great documentation. And it needed to ship binaries. So Python, if you guys don't know binary is just like, a compressed file format that holds all the code that's really great to ship stuff. And so none of the common scientific scripting languages did this. And it turns out that people that want to do this really write in like 4 languages, like C, Java, Go, and Rust. Java's not even, a binary, but it does compile to something. So what I did is I ended up looking at Go and Rust. And if you guys don't know Rust, it's a systems programming language by Mozilla, the same guys that make Firefox. And it's faster than Go by a little bit, but the string manipulation syntax is so terrible. I could never imagine anyone going from Python to that. It's just rough. Like, I've learned probably 20, 25 languages, done projects into my life. And like Rust was one of those things where it's like, dude, I don't want to do strings in this. No. So looking at Go, it shipped the binaries. It was fast enough. And it has a very similar Python syntax. And it's easy to set up. And it's easy to do releases. We actually have a bot that releases to like 14 different architecture operating system combos. So yes, we run on your machine. If it doesn't run on your machine, I don't know what machine you're using, but it's not from like the last 20 years. Unless it's Windows 95. We do not support Windows natively. You gotta use your Linux boot or whatever Isaac's using. I want to know what Isaac's using. Or Krishna actually made a great contribution where he made it so there's a Docker container in our, if you use VS Code will literally load the Docker container and run Poly from there with all the plugins that I use personally in development. So it just sets up your environment for you. So Go had all of these really great quality of life features, all these great, speed and power features, and it didn't really miss any of the libraries that Python already had. Funny enough, like it has a matrix library. It has, entire things for deploying machine learning models. And, I'm not always, it's not like I think that Go should be used for everything, but for this project, it made sense, essentially. So that's why I chose it. And it's been a real sticking point for a lot of people. They're like, oh, I don't want to learn a new language, but trust me, it's not that hard. It looks so similar to Python. It's silly. And it's pretty easy. It was made to be easy. Google actually made this language 10 years ago because like their developers were struggling with C and Python and they needed something in the middle that was not struggle town. Yeah, sorry. Is that a good review, Isaac?
Yep, definitely.
Yeah. Any other questions?
I think if anyone has other questions, my other question should be, sometime we discuss about how people that don't or they aren't developers, how they could help us actually.
Yeah.
So how Synthetic College that doesn't know anything about Golang and scripts could help us actually.
Let's see. There's request features and review pull requests. This is great. You don't need to know anything about code. All you need to know is a biological context and what's being done there. So if you're requesting a feature, I think Isaac Larkin actually requested something that if someone wants to write, it would be awesome. It's a non-repetitive parts calculator. And he gave a pretty good overview of what it is, how it works. And it's in our GitHub issues. It's a feature request. So if there's something you want that you think is generally useful and you don't know how to program it, go to the Polys repo, check out our issues, see what people are asking for. And if you don't see it there, make a request. And, it may be that I go, I don't really want to do that. But if you make a request, at least we know what people need. And that's immensely valuable. I mean, you're thinking, oh, Tim, it's such a small thing, just reviewing pull requests and requesting features. Nah, dude, that is amazing. That's like maximum reward for minimum effort. Like that is great. Just do it. Another thing that's been shocking, and I think this is something people should do more with people's projects where they know they're trying to work on it, but starring someone's GitHub repo is ridiculously helpful for some reason. It just search engine optimizes everything. And a huge amount of developers that we've had make pull requests literally found us on GitHub because we're the third highest project when you search synthetic biology tag. And that's just by stars. So that was so if for other people's projects, when I see someone's work and I really like it, I just star that, man. That is just free. That is just free help. And it feels dumb, but it's actually remarkably helpful. And there's a lot of stuff like that where it's low hanging fruit with a lot of payoff. Yeah. So yeah, that's pretty much everything. Unless someone's got another question, I always can chat. I think I'll just drop a link to our Discord. I'm sure a lot of you, I see so many faces I know already. So I'm sure a lot of you are there. And if you want to ask more about the project or look at the documentation or ask me things, because I kind of went through more of my philosophy of development and how this all came to be rather than, the nuts and bolts of how to do this. I'd be more than happy to talk about that another time.
Okay, so if we don't have any more questions, I think we could wrap this first one up. What do you think, Giovanna, Isaac?
I think only for finishing, I would like to say to people that we are actually using Poly for the Friendsime project, and we are already used for code optimization and also helping people in the design team to make good genetic parts. And I'm a little biased because I contribute to the project, but I think it's a great tool because most of the time I am a software engineer. Most of the time when I try to use software for synthetic biology in general, I don't have the same experience as a developer, as a front end or back end developer. And I think Poly give me this feel that I am actually having something familiar with developing and make good code for synthetic biology. So I really indicate people to use and see how they could resolve problems, use Poly, and have this experience firsthand.
Yeah.
So
And
yeah,
I didn't mention our users before, but we actually do have quite a few users or people from random companies that have just popped in and be like, hey, we're going to use this. So it turns out that there is a need. And I think a couple of YC Demo Day companies actually, unbeknownst to them, had their demo day stuff made with Poly via a consultant who is in chat, and I don't know if they can talk about that, so I'm not going to say anything more. So yeah.
Okay, so I think with that we can wrap up the first presentation. Thank you so much, Tim Stiles. It was an amazing speech. I'm pretty sure everyone here learned a lot.